In the earliest moments following the Big Bang, the universe was an incredibly hot and dense state where no complex structures could exist. Temperatures were unimaginably high, reaching trillions of degrees, and the energy density was so immense that particles existed in a chaotic, primordial soup. During this time, the universe was governed by extreme conditions that caused matter and energy to interact in ways that are not seen today. These interactions laid the foundation for everything that would come to exist. At approximately /10⁻⁻12 seconds after the Big Bang, the universe had cooled enough for the fundamental forces to separate. Gravity, electromagnetism, and the strong and weak nuclear forces, which had been unified during the earliest moments, began to act independently. This decoupling allowed the first subatomic particles to begin forming, including quarks, which are the building blocks of protons and neutrons. These particles moved at relativistic speeds, constantly colliding and interacting in an environment dominated by energy. As the universe continued to expand and cool, quarks started combining into larger particles. By /10⁻⁻6 seconds, quarks had formed into protons and neutrons through a process governed by the strong nuclear force. This marked a significant milestone in the formation of matter. Protons and neutrons are the basic components of atomic nuclei, and their creation set the stage for the development of the first elements. By the time the universe was about 1 second old, conditions had stabilized enough for neutrinos, light particles that rarely interact with matter, to decouple from other forms of energy. Around this time, the balance between matter and antimatter had tipped slightly in favor of matter, allowing the particles that survived annihilation to form the building blocks of the universe. This asymmetry between matter and antimatter remains one of the great mysteries in cosmology. As the universe approached its first 3 minutes, temperatures dropped to approximately 1 billion degrees. At this point, protons and neutrons began to combine through nuclear reactions to form the first atomic nuclei in a process called nucleosynthesis. During this brief window, most of the hydrogen and helium in the universe was created. Trace amounts of lithium and beryllium were also formed, though heavier elements could not yet develop due to the rapid cooling of the universe. The formation of these light elements was a delicate process. The ratio of protons to neutrons determined the abundance of hydrogen and helium. Neutrons were slightly less stable than protons and decayed into protons over time, meaning that the number of neutrons was gradually decreasing. This decay, combined with the nuclear reactions occurring in the early universe, resulted in approximately 75% of the mass of the universe being hydrogen and 25% being helium, with only trace amounts of heavier elements. After about 380,000 years, the universe had cooled to approximately 3000 Kelvin, allowing electrons to combine with nuclei to form neutral atoms. This process, known as recombination, marked a significant shift. For the first time, photons were no longer constantly scattering off free electrons, allowing light to travel freely through space. This event created the cosmic microwave background (CMB) radiation, which serves as a snapshot of the early universe and provides critical evidence for the Big Bang theory. The hydrogen and helium atoms formed during this period became the primary ingredients of the first stars and galaxies. Under the influence of gravity, these atoms began to coalesce into dense regions, leading to the formation of stars. Inside these stars, nuclear fusion processes would later create heavier elements, enriching the universe and paving the way for planets and life. The simplicity of the early universe's composition, primarily hydrogen and helium, was a critical factor in its evolution. These elements, being light and abundant, were able to cool efficiently and form the first structures under gravitational influence. The formation of stars from these elements initiated a cascade of cosmic events that shaped the universe's large-scale structure. As stars began to form, they emitted light and heat, changing the dynamics of their surrounding environments. Some of these early stars were massive and lived short, violent lives, exploding as supernovae and dispersing heavier elements into space. This enrichment of the interstellar medium set the stage for the formation of more complex structures, including galaxies, planetary systems, and eventually, life. The early universe also experienced fluctuations in density that were amplified by gravitational forces. These fluctuations, which are observed in the CMB, were the seeds of galaxies and clusters. Regions with slightly higher densities attracted more matter, eventually forming the vast cosmic web of structures we see today. Despite its simplicity, the early universe was remarkably dynamic. The interactions between particles, forces, and energy created a highly active environment where the building blocks of matter were forged. These processes, though chaotic and violent, followed precise physical laws that scientists continue to study to understand the origins of the cosmos. The story of the early universe is a testament to the power of fundamental physics. It reveals how simple elements like hydrogen and helium, formed under extreme conditions, became the foundation for the complexity we observe in the universe today. From the tiniest particles to the largest structures, the early universe set the stage for everything that followed. The formation of the early universe was not an isolated event but part of a larger continuum of cosmic evolution. The processes that created the first particles, elements, and structures are interconnected with the ongoing dynamics of the universe. This connection underscores the importance of the early universe in shaping the cosmos we inhabit. Understanding the early universe provides insights into fundamental questions about existence, the nature of matter, and the forces that govern the cosmos. It also highlights the remarkable ability of science to unravel events that occurred billions of years ago, offering a glimpse into the origins of everything we know.
The Cosmic Microwave Background, CMB, is one of the most compelling pieces of evidence for the Big Bang Theory. It represents the faint afterglow of the immense energy released during the universe's creation, a relic from the time when the universe was in its infancy. This radiation is a snapshot of the universe approximately 380,000 years after the Big Bang, marking the moment when matter and radiation decoupled, and light could travel freely through space for the first time. When the universe was in its earliest stages, it was an extremely hot and dense plasma composed of subatomic particles and photons. These photons were constantly scattering off free electrons, preventing light from traveling long distances. This created an opaque environment where radiation and matter were tightly coupled. However, as the universe expanded, it cooled. By the time it reached about 3000 Kelvin, electrons began to combine with protons to form neutral hydrogen atoms, a process known as recombination. The formation of neutral atoms allowed photons to travel freely, marking the transition of the universe from an opaque plasma to a transparent state. The light released during this transition is what we now detect as the CMB. Though originally emitted as high-energy radiation, the expansion of the universe over billions of years has stretched its wavelength, transforming it into the faint microwave radiation we observe today. The CMB is remarkably uniform, with a nearly consistent temperature of about 2.7 Kelvin across the entire sky. However, tiny fluctuations in this radiation, on the order of a few millionths of a degree, are also present. These fluctuations are the imprints of density variations in the early universe, which later gave rise to galaxies, stars, and the large-scale structure of the cosmos. By studying these small variations, scientists have gained valuable insights into the composition, age, and evolution of the universe. The discovery of the CMB was accidental. In 1964, Arno Penzias and Robert Wilson, while working with a radio antenna at Bell Labs, detected a persistent, uniform noise they could not explain. After ruling out other sources, they realized they had stumbled upon the CMB. This finding provided a crucial confirmation of the Big Bang Theory and earned them the Nobel Prize in Physics in 1978. The CMB serves as a powerful tool for cosmology, allowing scientists to probe the conditions of the early universe with unprecedented precision. Observations of the CMB have been made by several missions, including the COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and the Planck satellite. These missions have mapped the CMB in extraordinary detail, revealing not only the tiny temperature fluctuations but also the polarization patterns of this radiation. One of the most significant insights from CMB studies is the confirmation of the universe's flat geometry. The temperature fluctuations observed in the CMB match the predictions of a flat universe as described by general relativity. This finding supports the inflationary model, which proposes that the universe underwent a rapid exponential expansion shortly after the Big Bang. The CMB also provides critical information about the composition of the universe. By analyzing its fluctuations, scientists have determined the proportions of ordinary matter, and dark energy. Ordinary matter, which makes up stars, planets, and life, constitutes only about 5% of the universe's total mass energy content. Dark matter accounts for roughly 27%, and the enigmatic dark energy makes up the remaining 68%. Another remarkable feature of the CMB is its isotropy, the nearly uniform temperature observed in all directions. This uniformity poses a challenge to the classical Big Bang theory, as regions of the universe should not have had enough time to come into thermal equilibrium. The theory of cosmic inflation resolves this by suggesting that all regions were once in contact before rapid expansion stretched them apart. The CMB is not just a snapshot of the universe's past, it also provides a window into its future. By studying this radiation, scientists have developed models that predict the ultimate fate of the universe, whether it will continue expanding indefinitely, collapse in a big crunch, or reach a stable state. The study of the CMB has revolutionized our understanding of the universe. It has confirmed the Big Bang theory, validated the inflationary model, and provided precise measurements of the universe's age, currently estimated at 13.8 billion years. It also offers a framework for understanding the formation of galaxies and other large-scale structures. Despite its immense significance, the CMB remains a faint signal, detectable only with advanced instruments. It serves as a reminder of the universe's humble beginnings, when it was a hot, dense plasma that has since evolved into the vast, complex cosmos we observe today. The CMB's importance lies in its ability to bridge the past and present. By decoding its patterns and properties, scientists can reconstruct the early universe's conditions and connect them to the structures we see now. It is a cosmic time capsule, preserving the echoes of the Big Bang and offering endless opportunities for discovery. As research continues, the CMB will likely unveil even deeper mysteries about the universe's origins and evolution. It is a testament to the power of observational science and a cornerstone of modern cosmology, reminding us of the profound and interconnected story of the cosmos.
The formation of galaxies and stars is a captivating chapter in the universe's history, showcasing the intricate interplay of gravity, matter, and time. After the Big Bang, the universe was a vast expanse filled primarily with hydrogen and helium. These primordial elements, born from nucleosynthesis in the first few minutes of the universe's existence, were evenly distributed but not perfectly so. Small density fluctuations in the early universe created regions where matter was slightly denser than its surroundings. Over billions of years, gravity began to amplify these fluctuations. Regions with higher density attracted more matter, gradually forming vast clouds of gas. These gas clouds served as the seeds for what would become galaxies and stars. As matter accumulated, gravitational pressure increased, causing the gas to heat up. This process marked the beginning of star formation. The formation of the first stars, known as Population 3 stars, was a transformative moment. These stars were massive and short-lived, burning their fuel rapidly and ending their lives in spectacular supernova explosions. Despite their brief existence, these stars played a crucial role in enriching the universe. They created and dispersed heavier elements like carbon, oxygen, and iron, which are essential for the formation of planets and life. Galaxies began to form as gravity pulled vast amounts of gas, dust, and dark matter into larger structures. These early galaxies were irregular in shape and size, gradually evolving into the diverse forms we see today: spirals, ellipticals, and irregular galaxies. The Milky Way, our home galaxy, is a spiral galaxy containing billions of stars, including our Sun, which resides in one of its spiral arms. Stars within galaxies are born in stellar nurseries, dense regions of gas and dust known as molecular clouds. These clouds collapse under gravity, forming protostars. As the protostars accumulate more mass, nuclear fusion ignites in their cores, producing the light and heat that characterize stars. The balance between gravitational pressure and the outward force of nuclear fusion maintains the stability of stars throughout their lifetimes. Over time, stars form in clusters and associations, often influencing each other gravitationally. Massive stars, which burn their fuel quickly, can end their lives in supernovae, creating shockwaves that trigger the formation of new stars in nearby regions. This cyclical process of star birth and death enriches the surrounding medium with heavier elements, fostering the development of complex structures. Galaxies are not isolated entities. They interact with one another in dramatic ways. Collisions and mergers between galaxies are common, leading to the redistribution of stars, gas, and dark matter. These interactions can trigger bursts of star formation, creating regions teeming with young, bright stars. Our Milky Way is currently on a collision course with the Andromeda Galaxy, a process that will unfold over billions of years. The evolution of galaxies and stars is closely tied to the role of dark matter. Though invisible and undetectable directly, dark matter exerts a gravitational pull that influences the formation and structure of galaxies. It acts as a scaffolding for the visible matter, guiding the growth of galaxies and the clustering of stars. Stars are not eternal. Smaller stars, like our Sun, will eventually exhaust their nuclear fuel and evolve into white dwarfs, leaving behind planetary nebulae. Larger stars can collapse into neutron stars or black holes after supernova explosions, dramatically altering their surroundings. These remnants are reminders of the powerful forces at work in the cosmos. Planetary systems, like our own solar system, form as a natural byproduct of star formation. Disks of gas and dust surrounding young stars coalesce into planets, moons, asteroids, and comets. These systems are the nurseries of potential life, made possible by the heavier elements produced by earlier generations of stars. The diversity of galaxies and stars we observe today is a testament to billions of years of cosmic evolution. From the smallest red dwarfs to the largest spiral galaxies, each celestial object tells a story of formation, interaction, and transformation. Together, they form the vast cosmic web that defines the structure of the universe. Studying galaxies and stars not only helps us understand the universe's past, but also provides insights into its future. The distribution and behavior of galaxies offer clues about the ultimate fate of the cosmos, whether it will continue expanding indefinitely or experience a different end. The journey from primordial gas to the stunning complexity of galaxies and stars is a remarkable testament to the power of natural processes. It underscores the interconnectedness of all matter and energy, revealing a universe that is both dynamic and deeply interwoven. Each star and galaxy is a window into the cosmos's history, offering a glimpse into the grand narrative of existence.
The ongoing expansion of the universe is one of the most profound and essential discoveries in modern cosmology, offering strong support for the Big Bang Theory. The realization that the universe is expanding is a relatively recent development in the history of science, and it has transformed our understanding of the cosmos. This expansion is not just a theoretical concept but a phenomenon observed directly through the redshift of light from distant galaxies, providing a compelling piece of evidence that the universe had a dynamic and ever-evolving beginning. The key observation that led to the discovery of the universe's expansion came in 1929, when the astronomer Edwin Hubble analyzed the light emitted by galaxies. He noticed that light from galaxies further away from us was shifted toward longer wavelengths, or the red end of the spectrum. This phenomenon, known as redshift, occurs because the space between us and the distant galaxies is expanding. As light travels through this expanding space, its wavelength stretches, causing the light to become redder. The more distant the galaxy, the greater the redshift, indicating that it is moving away from us at a faster rate. This redshift was a crucial piece of evidence that the universe was not static as had been previously thought. Instead, it showed that galaxies were receding from one another with their speeds proportional to their distances. Hubble's observation suggested that space itself was expanding, not just the galaxies moving through space. This observation led to the formulation of Hubble's law, which mathematically describes the relationship between a galaxy's distance and its velocity. The law provided a direct measure of the rate at which the universe is expanding. The implications of an expanding universe are profound. It means that the universe had a beginning, a moment when all matter and energy were concentrated in a single point, the singularity at the origin of the Big Bang. If the universe is expanding now, it must have been much smaller in the past, and if we trace this expansion backward in time, we reach the conclusion that the universe began from a highly dense and hot state. This idea of a dynamic universe, constantly evolving and expanding, aligns perfectly with the predictions of the Big Bang Theory. The ongoing expansion is not just a relic of the past. It is an active, ongoing process that continues to shape the universe we observe today. The expansion of space is causing galaxies to move away from each other, and as a result, the universe is becoming less dense over time. However, this expansion is not uniform across all scales. On smaller scales, such as within galaxies and galaxy clusters, gravitational forces are strong enough to overcome the expansion, allowing these structures to remain intact or even merge. But on cosmological scales, the expansion continues unabated. One of the most fascinating aspects of the ongoing expansion is that it is accelerating. In the late 20th century, astronomers discovered that the rate of expansion of the universe is increasing, rather than slowing down as had been expected. This surprising result came from observing distant supernovae, which appeared dimmer than expected, indicating that they were farther away than anticipated. This observation led to the conclusion that an unknown force, called dark energy, is driving the accelerated expansion of the universe. Dark energy is a mysterious component of the universe, constituting about 68% of the total energy content. Its exact nature remains one of the greatest puzzles in cosmology. What is known is that dark energy has a repulsive effect, counteracting the attractive force of gravity and causing the expansion of space to speed up. The discovery of dark energy and the accelerated expansion of the universe have profound implications for the future of the cosmos. The expansion of the universe is also tied to its large-scale structure. As the universe expands, galaxies cluster together due to gravity, forming galaxy groups and clusters. These large structures are connected by vast cosmic voids, regions of space that are relatively empty. The interplay between the expansion of the universe and the gravitational attraction between matter has shaped the cosmic web, the vast, interconnected structure of galaxies and galaxy clusters that defines the architecture of the universe. The expansion is also influencing the fate of the universe. If the expansion continues indefinitely, the universe will keep growing larger and colder, eventually becoming a cold, dark, and empty place. This scenario, known as the Big Freeze, suggests that stars will burn out, galaxies will drift apart, and the universe will approach a state of maximum entropy. Alternatively, if the expansion were to slow down and eventually reverse, gravity might cause the universe to collapse in a big crunch. However, current evidence suggests that the accelerated expansion driven by dark energy will continue, making the Big Freeze the most likely outcome. The study of the universe's expansion also provides a way to measure its age. By studying the rate of expansion, scientists can estimate the time since the Big Bang. This estimation, combined with other observations, places the age of the universe at approximately 13.8 billion years, a figure that has been refined through measurements of the cosmic microwave background radiation and the distribution of galaxies. The ongoing expansion of the universe has opened up a new frontier in cosmology. Observing how galaxies move, measuring the rate of expansion, and studying the effects of dark energy are all key areas of research. The expansion provides a deep connection between the present and the distant past, as it allows scientists to trace the history of the universe and its future evolution. In summary, the ongoing expansion of the universe is a key piece of evidence that supports the Big Bang Theory. The redshift observed in the light from distant galaxies, the discovery of dark energy, and the accelerating expansion all point to a dynamic, evolving cosmos. The universe is not static. It is continually growing and changing, and understanding this expansion allows us to glimpse the vast, interconnected story of the cosmos, from its explosive beginning to its ever-unfolding future.